Morning, Pam.
Morning, David. How
How are you? How's things?
Good. Not too bad.
That's good. That's good. Any fun stuff at work happening, or?
I was just there actually in Edmonton for a few days. I went there on Wednesday, just got back yesterday. Yeah, it was fun seeing the city and meeting the co-workers face to face for the first time.
Well, that's good. So you haven't been there before?
Not since I started working there.
Okay.
I've been to Edmonton before, but not to the office.
Did you grow up here in town, or?
Since high school, I came here when I was 16, but been here since. Yeah.
I came here when I was 16, then I went back to Australia, then I came back. So yeah.
Okay, cool. Yeah, Australia is one of those places I like to go, but the flight is just super long. I don't know if I can handle it.
It's really long. Yeah, it's pretty good. So Rob should be joining us. Rose has to do an exam today, so we can keep it short if you like, or we can go into this stuff. I'm really interested in this stuff. I'm not sure if you've looked at...
Sorry, I was traveling, so I missed your usual message.
Oh, that's fine. No. I'm just digging into this whole idea of conditional independence being the definition of thingness, and basically trying to interpret graphs, trying to essentially develop an intuition so that when we look at graphs, we can partition them. Like we've been looking at clustering. So we've got a bunch of points in space, and we have some metric by which we can measure distance between them. And I'm trying to generalize that to, we have a category with some points in it. Oh, here it is. Let Rob join.
Hey, Rob.
Hey, Rob. You're muted. No, you're still muted. Oh, that's not good. Oh, there we go.
Good morning.
Morning.
No, just Pam's been to Edmonton, so he went and visited his team this week. Have you been to Edmonton, Rob?
Never have.
Me either. I've been to Calgary a bunch of times. I've just never been to Edmonton.
Yeah, Edmonton is smaller, so and it's generally way colder. But yeah, when I was there, it was nice. So.
Okay. Cool.
Yeah, I like Canada.
Me too. But yeah, so basically, we're still talking about clustering in my mind. One of the mechanics by which you can cluster things is a metric or a distance. So if you have some distance you can measure between things, then if you have a bunch of things that are close together, and you have a bunch of things that are further away from that, you can basically infer that this is a thing and it's distinct from these other things, maybe. And what the free energy stuff talks about, which is Perlian, is that essentially interventions are sparse. Okay, so there's different ways of thinking about this. So if you think about it from a categorical perspective, you could say that the arrows that join one set of points to another are way fewer than the arrows that join points in the same thing to each other. So if I have a densely connected region over here where there's a lot of points which have arrows between them, and I have another group over here, but there's only a few arrows in between, then the inference is that this is one thing and this is another, because they're essentially conditionally independent. And if that connectivity climbs and gets to some threshold, then we would say that the things are not distinct.
How do you relate that to clustering? Sorry, I missed.
So the intention is to try and get to some kind of equivariance, right? So if you think about a training sample of cats and dogs, right? So all the images that have cats in them are equivariant. In other words, if I say the word cat and it produces one of the images of the cats that we've given it, or it synthesizes some new image of a cat, and we see that as a cat, then we could say that that is equivariant with other pictures of cats, right? They essentially have the same catness to them. So what we're trying to do is we're trying to take many points and collect them together into fewer points, right? So we have, instead of 1 million points, we have 2 things. And then that makes a data set comprehensible to human beings. So this isn't about being right. This isn't about statistical perfection. This is about understandability, right? We can grasp a few things. I can't grasp more than like 7, I think is the magic number. So if we can take a dense data field and we can simplify it down into less than 7 things, then we can understand it. So this is about human understanding. This isn't about some statistical test that we can make. So how do we take something that we can't understand and make it understandable? Well, we look for equivariance and we try and break the thing up into bigger things or categories or clusters or groups or whatever you want to call them. And then if we can get that number down small enough, then we can essentially understand it and build models of it and use it in our daily lives.
So I wonder, like, if you didn't know a picture was a cat or a dog and you went about doing your clustering, I suspect you're not going to get them separated. So I guess the trick is, how are you actually going to do this? Yeah, the sentiment I think you said is basically the whole goal of machine learning since it started. But I guess I'm wondering how you actually go about doing it.
So when you run that deck example, that the paper that you brought up, I have it right here. I can bring it up. Let me do that.
Well, tell them about your MNIST example.
That's the one I was going to bring up, yeah.
Okay.
So, yeah. So in the MNIST example, let's do this.
Sorry, it's late breakfast here for me, guys.
Oh, no problem. No problem.
Don't worry about it.
This one. Okay, so we have this cool data set here. This is MNIST fashion.
Yes.
So I'm sure you've heard of it. And this is the world's simplest neural network. Basically, this is one of the PyTorch example sets. And all you're doing is you have basically this. So you have a linear layer, ReLU, linear layer, ReLU, linear layer. Super simple, nothing interesting. And then when you go down here, you'll see that it's actually able to get pretty good accuracy, 71% on a bunch of images.
So what are you running? You're running DEC on this?
No, this is not DEC. This is just a very simple example. All right, and then the DEC example is true MNIST.
So here you're just classifying.
I'm just basically, yes. Sort of, like
so
it's a one-hot
using
encoding.
So you are using the labels.
Yeah, this is trained data.
Yeah.
Okay, and then we'll come back to this, but I have another one here, which I'm not sure if I change. Do you see me change panels in the web page? I don't know.
Yeah. I see Jupyter now with the files.
Yeah, that's great. Okay. And so the one I wanted to bring up was, where is DEC? I have it here. Not this one, is it? No, something else. Sorry. Where's the DEC stuff? Is there arena test? I have it. I'm not seeing it. Anyway, guys, I'll hunt for it so you don't have to stare at me fiddling around. But the DEC example, basically what it did, and that's because it's command line only, sorry. Yes. So the DEC example, I can't run it in a notebook, it's not designed for that, so you have to run it as a command line tool. And the covariance matrix, which I do have, which I will share, is the interesting part. So let's bring up the covariance matrix, sorry. So where is the covariance? One sec. Okay, there it is. I'll have to hunt for it. But essentially, okay, so the covariance matrix for the unclassified MNIST data, the DEC example, got most of it right. It got 9s confused with 4s, it got 7s confused with 1s, and it got a few other bits and pieces here and there. Yeah, so it does sort of work. So there was correlation between the categories that humans would have used and the unsupervised categories. There was correlation, but it didn't have the nuance that we have, right? So we can distinguish 7s from 9s and 1s, and we can distinguish 4s from 9s most of the time.
I guess that's as expected, right?
Right, but essentially it's a, what's the word for it, timeless data set. There's no sense of sequentiality, there's no sense of action, there's no sense of intervention, nothing. It's just, we saw some stuff and it looks like this other stuff because if I measure the distance between them, I get a close distance. You know, that's the only kind of metric, the only means by which we can simplify the data. All we can say is the data that was close to, if we clump together the data that was close, then we can reduce the number of things down. What the free energy principle is trying to say is that if you can up your game to include an action space, some sort of functions like in category theory, then there is a different mechanic by which you could group things together. And that is densely connected things lumped together, and sparse interactions essentially form boundaries.
So how are you thinking about like actions and their relations to these clumps? Because to me, those are totally different problem settings. Like one is sort of reinforcement learning if you want to do actions, or other sort of dynamical system. This one is the supervised or unsupervised learning problem. I don't see any link between them, I guess. It's not clear to me how you want to add actions by, I guess I haven't seen it. It might be very useful if you can do it, but I can't think of how you would go about doing clustering with any sense of action. So what is an action in a clustering algorithm?
I'll bring up my boring picture again, and we'll talk about this. It's very, very relevant. So an action simply means that it's a state change within the object, in my mind, right? So I was in this state, I'm now in this state, and
yeah, but what are you trying to cluster that there's time aspect to it? I guess maybe that's related to your financial stuff you're working on?
It's related, absolutely, okay. It's related, yeah.
Yes, yes.
So let's talk about precursors very quickly. One of the things that Rob and I have been looking at is something called liquidity events, and I'll get Rob to describe that because he can do a better job than me. But liquidity events are essentially a situation where, Rob, do you want to kind of give Pam a quick primer on liquidity?
Yeah, so here's sort of the use case that got us started in this. You want to trade a large block of stock, and the act of you trading is going to impact the market price. So if you're trying to sell a whole bunch of stock all at once, then you're going to see that the market is going to try and infer information from you making that trade, like you think there's bad news. Now, if you step back from that and kind of generalize it a little bit, you can think of, okay, there are times when there's a lot of people actively involved in the market. If I want to sell something, I can sell it pretty easily. So that would be a high liquidity time. Alternatively, there are times when there's sort of nobody else around. If I try and sell it, I'm going to get an inferior price. That'd be a low liquidity event or period. So what we were trying to do is, I've got a whole bunch of data on different measures of liquidity, quote unquote. And we were trying to see if there were clusters of them, in that, can we characterize sort of high liquidity, low liquidity? And then is there some sort of mechanism that kind of leads us to believe you're going to move from one to another?
Do you know which one is which, just based on your domain expertise looking at the data, or we don't know?
More or less, yeah.
So can't you just use that as a label and create a classifier that gives you high liquidity versus low?
Could potentially.
No, that's exactly what you're talking about. Yes, this is it. Yeah,
Kind of awkward because the dimensionality is so high. So in the data
but the algorithm will take care of the dimensionality. You don't need to worry about it. As long as you have the labels of high versus low liquidity, that's all you need. It's like 3 lines of code, right?
Yeah, but we don't really have that.
Okay.
So we've got this, it's like 180 variables or something, and they're all kind of correlated and they're all kind of trying to measure the same thing.
No, I remember we talked about this, I guess. So usually when you have a bunch of highly correlated variables you want to use for prediction, I mean, you don't have to, but you can do PCA and remove most of them, right?
Yes, so that's clustering. So PCA is a kind of clustering. I'm not disputing with you and agreeing. Yes. Right, so if you look here, you'll see that all of these different metrics are very, very highly correlated, right? These are very highly correlated. If you take out the one outlier, these are very highly correlated, right? So there are literally like 40 different metrics of volatility, of liquidity, and they're all essentially the same.
I mean, you could just use all of them, but that basically means you don't have 40 indicators, you have one. So that's your data.
Okay.
Yeah, so where I was going with it, which is, if I'm basically the same as something else, then my weight should be adjusted, right? So if I replicate my data 1,000 times in my data set, I don't want the other 999 occurrences to overly bias the system, right? So I'm trying to define, so the goal of the project here is best expressed in this picture, which is we want a humanly interpretable number of these parameters so that if I show you this value, and this value, you can kind of come up with an intuitive assessment of what's going on and act on that intuitive assessment, because it's the human being that's doing the decision making. If I show you 190 variables, it doesn't mean anything.
So I guess the question is, why do you care about an intuitive assessment? Like if you want to make a trading decision, and do you really need intuition? Because going back to, I think the comment you made earlier, David, about like 7 things we can, like our brains are limited. So if you want to put the constraint that you want to understand everything you're implementing, then you have to oversimplify and trade off with performance, right? Is the goal to understand why something is more, like sometimes are more liquid or less, or is it to make a decision to make money?
Well, at this point, it's the latter, but the two are not independent for the following reason. What we're really interested in is creating a predictive model of what this liquidity is. So, think of it at time T, you decide to trade, but you can't execute that until time T plus 1.
Mm-hmm.
So in that sense, being able to explain what drives it, how it moves. So you're in the low liquidity state now. What's the likelihood you're going to be in the low liquidity state next period? If that's high, then you don't do the trade.
But is that all you need to know? Like, what is the probability that you're going to be in high liquidity, or do you need to know why the model thinks you're going to be in that state in T plus 1?
Well, I would say it's primarily, what's the probability?
Yeah, so basically it's just as you said, a predictive model, right? So you don't want an explanation. If you want a story around it, that's a different story. Like you want intuition of, okay, this price went up, that's why we think it's going to be high liquidity. And this has happened 5 times in the past. Like if you want a story around it, I guess that's a different story. But if you just want to know what is the likelihood of you being in high or low liquidity X time steps from now, then that's a much simpler problem, right? You just throw the data and you get a model. You don't need to understand it. You can assess it and see how accurate you'll be on average, but.
Okay, so there's a statistical element, which I'm not disputing. Yes, your statistical intuitions are bang on. But there's also a human factors thing, right? Which is, would I put 20% of my net worth into a black box, hit a button and walk away and not care to understand what it was doing with my money?
But I wouldn't even do it if somebody gave me a story, because I trust the story as much as you trust those numbers, right? I mean, how do you trust that story?
Well, if you don't trust anything, then you'll never trade. So you kind of have to play a game here. I'm trying to. Well, I guess my goals might be subtly different than Rob's. I think they are the same in a subtle way, but it is subtle.
Well, okay, so to me, I mean, I don't see them as necessarily different, because if I can create a predictive model, I can kind of go inside the black box and try and understand what's going on and why.
But in general, that's not true. I think if the model gets complicated enough, like you trade off between your prediction accuracy and explainability usually. So you need to decide which one you care more about. It. I totally agree that if you have a highly like 100% predictable model, right? Of course, it's learned something that it has something to do with reality. So then you can go in and try to figure out why. But in general, you could have millions of features, right? So maybe in your case, it's possible to go have a look. But in general, that's not possible. So you need to decide whether you care about practicality of it, or you want to understand something from like a scientific or whatever perspective.
Yeah, you got a million variables. You can't sort it out. Maybe with 200, you can't sort it out either. But there are things you can do. So for example, you can try and take small changes in the input variables and see what happens to your predictive model.
Yep. Yeah, they do that. So that I think they're called saliency maps. Like there's sort of many different techniques for like doing exactly what you propose.
Mm-hmm.
I'm not, once again, my goal is, well, our goal is not to say that we've created something totally new. We're trying to apply what we know to this liquidity problem. And we're also trying to develop an intuition, because the means by which we could confer this information to others isn't by producing a black box, it's by explaining it to human beings, right? So can we explain the system? Can we explain large systems? Like, this gets back to the whole question of explainability at all. Like, is it even useful to take 1,000 parameter thing and jam it into 7 parameters and come up with an explanation that people understand? Arguably, yes, I would say. I don't think it's a complete waste of time. But I guess if your goals aren't clear, then I don't know. Also, we might want to consider trying to bring the intuitive process into machine learning itself, right? So if we're trying to specify a value function or a reward function or loss function, whatever you want to call it, we have to be able to confer this to the machine in a way that it understands and can, interpret correctly. And so how do you take 1,000 parameters and come up with a reward function that actually makes some sense? That's an interesting question.
But reward function is usually have nothing to do with what parameters you have. It's something you care about that you want to maximize or optimize, or it doesn't have to do anything to do with your features. Like you want more money, you want whatever higher liquidity or whatever you want. That's usually outside of what data you're using. Am I missing something?
Maybe not. Maybe I'm missing something. I don't know. Once again, this is a discussion.
I mean, that's why I love these discussions.
Right.
But no, I mean, they're not. I can certainly imagine situations in which you know, the reward function is really kind of predicated on the observational data you got.
But the reward value is, but not the reward function. Can you give me an example of why in a case where your reward function has something to do with your variables?
Clustering. But what's the reward function for a clustering?
But it's unsupervised. There is no metric. But that's the whole point. That in unsupervised, there is no metric. So that's why it doesn't work most of the time, because you don't know what you're looking for. So there's nothing to optimize. So in your case, I guess in a like K and N, I guess the reward function is that distance between the clusters or whatever. You can, like as a loss function, you want to put the things that are closer. So if you have two clusters, if you have them denser and farther apart, that's the best possible way of your cluster. So, but that again is a matter of what you decide a distance is. So that's your reward function. You put in the reward function by specifying your notion of distance, right?
Right. Yes. Yes. Yes.
It goes back to the Hume's like is versus odd, right? Like to me, like reward and loss is the odd part, what you want. And then the data gives you what is, and then you try to connect the two.
Or we get a machine to try and connect the two, which is, I think, the point, right? It's not us, it's the machine.
You still have to decide what you care about. The machine can't tell you what you care about. There's no way you can, from the data of cats and dogs, the machine can't learn that you want to separate cats from dogs. Maybe there's infinite number of ways you can separate those images. Maybe you want to separate images that have a green background versus black background. You don't care at all about cats and dogs. Like that's a very valid something to want, right? So it's just a matter of you have to decide what you want first.
Can we develop the underpinnings of intuition so that the machine itself will develop an intuition for what it wants, as it were? This is kind of a circular argument, I'll be the first to admit, but
is that a matter of intuition? I guess like what you want is that a matter of intuition? I don't know.
It's kind of like we try a classification on for size. So a group groupings, mapping the world into groups or clusters. And then we try another one. And which one seems to generate better outcomes for us?
Yeah, so you have to specify what the better outcome is. That's your reward. If you say, I want the machine to tell me what's better, whether I have more money or less money, then that's it. I don't think anybody can do that. Like, so you decide what you want first out of your data set, no?
So that's where I'm trying to get to. The first thing you said. Yeah.
Maybe we're saying the same things. I mean, maybe, so you're trying to see, we still want to maximize our money, but maybe you want to see how do I cluster my data points in a way that helps me do that better. I think that I understand. Like maybe the machine can go through different processes of your data in a way that helps you maximize your money. But there are multiple ways of doing it. And that's what we're trying to figure. We don't know whether classifying things into high liquidity and low liquidity is the best way to go. Maybe there's 3 classes of types of liquidity. And if you cluster it into those 3, then it will help you maximize your money better. So that I understand. But if you say you want the machine to tell you that you should want more money, I don't know if you're going to get that.
Once again, we're playing with this. I'm exploring here. So, so I think that the investor, sorry, go ahead, Rob. Yeah.
No, just the observations are well stated. Yeah.
So where I was going was, I think that the investor is part of the network, right? If the network can't give you information that you can believe that will cause you to invest to make more money, then the network itself is failing. Okay, because you are inherently wound into it. So there is a restriction in the network where it has to produce an explanation or an argument or a picture or something that will give you the confidence to move ahead with the trade over time, right? This is game theory, kind of backwards and forwards action space. So I gave you a prediction, you acted on it, you lost, you didn't use me anymore, I have failed, right? So there's this like it's two agents trying to come to a common understanding. Like you can't just take the human out of the loop and create something and shove it in the corner and turn it on and assume that anything meaningful is going to happen. Right? We're wound into this.
No, but no, I think that's fair. But I'm curious, like, let's say as a personal, as a user of one of these investment, whatever, let's say Rob makes this amazing investment platform based on these models and you get access to it. So you're saying you're more likely to pay subscription and use it if the engine spits out a couple of sentences of why you should be investing.
It convinces you to invest in whatever means, by whatever means that might be, right?
But couldn't it be just a track record over the past 6 years that 90% of this advice that the machine gave you was correct and 10% was wrong, and you decide whether you want to take it or not, and that's all you can get? To me, I guess as an investment, that's enough confidence for me to know what are the chances of success. Like if somebody gives me a long narrative of why the model thinks this is a good time to invest, that does not do anything to convince me. I want to see the numbers, but maybe that's personal. That's why I'm asking you, like you would prefer like a more detailed accounting of why the algorithm wants you to invest?
If people are happy to take the machine's predictions on faith, and that is a benefit to the people for them to do so, then
but it's on faith anyways, isn't it? Like you have to have faith on the story or the number. Like it's the same, all of it's all on faith.
Yeah, but I'm glad we're having this conversation because it's forcing me to think through this. But my confidence is really going to be based on two things. It's going to be based on, whether it seems to work and whether I can tell a believable narrative about it.
Right. Yeah, I
so
agree.
It's funny how you put it that way. Like, so is that all the requirement, that it has to be a believable narrative, or does it have to have anything to do with the truth? Because it's totally possible to generate narrative post hoc after the number is generated to make it sound plausible.
Yeah, absolutely. And I guess I view these sort of as complementary measures. But yeah, I mean, you're right. I'm kind of mixing and matching apples and oranges.
I mean, I could see one reason, like let's say the investment strategy, your model tells you, okay, dump all your Tesla stock like today. Like you rightfully would be skeptical, right? I mean, Tesla has been, I don't know how Tesla is doing. I'm assuming they're doing well. I know they dropped a little bit, but let's say they're doing well. You would be rightfully surprised, and you might want to know a reason, like why should I do something so drastic? Give me a reason. And if you don't get it, you might choose to ignore the algorithm, right? Like in extreme cases, like if your intuition, it says I should hold on to Tesla based on your previous experience, and the model says I tell you 99% of the time you should dump all your stock and gives you no reason, I can see most people wouldn't take that advice, right? So maybe in those cases it makes sense. But yeah, so you would be convinced if somebody tells you, yeah, we just heard the news that Elon Musk is gonna like resign as a CEO of Tesla tomorrow, then you know why you should be dumping your Tesla stock. So then it would make perfect sense to you, right?
Yeah.
Or the machine might say, I don't know what's going to happen next. Don't ask me. Because it doesn't, right? Because we've moved into a period of volatility where prediction, like some new, we've detected the presence of new information in the market. And that has now essentially told us that the predictive power of the model is greatly reduced, right? That's kind of a meta model. And once again, there's a human being in the loop, right? We're trying to create human-machine synthesis. And one of the things the machine has to do, which takes us back to clustering, is to make it comprehensible by humans, which is not to produce a 50,000 million page document explaining why it thinks you should not do something.
Yeah, but I would be worrying about that objective, right? Like if you task the machine to make this comprehensible to a human, there are, like, you're not putting the constraint that it has to have anything to do with the truth. And the machine can probably figure out a good way to put a story so that to get the humans to.
I know, but if it gets it wrong, then that's a penalty to the machine because its survival will end. It will
Yeah,
go
but
extinct.
sure,
I
sure,
tricked
but
you into buying the wrong stock. Haha.
no. But the confidence the machine knows, right? So the machine doesn't understand anything. So it knows, let's say 90% of the time, this prediction is going to be correct. But based on that, it could generate an explanation that has nothing to do with the truth, but to convince you that it's the correct one. And the probability of being wrong is still only 10%. So that's always going to be.
So maybe it was the
there.
right choice for you to invest, which means that the model is doing its job well.
Yeah, but it's tricking you, right? Like it's tricking you.
Maybe
like,
that's what's needed, right?
Yeah, that's my question. Like that's why I don't trust stories. I trust the number. I don't want to know the story the machine wants to tell me.
Well, I mean, generally the stories are, explaining the past and not predicting the future.
Right.
And it's really easy to predict the past.
Easier, yeah.
Although that's actually a separate question. That's a deeper question. Can you basically run time backwards and generate predictions of the past? But leave that aside for the moment. So if there's an unconditional likelihood a prediction is going to come true. I mean, the likelihood we'll all get together next week is very high. So in that sense, that would be a good prediction. But in things like, I guess one of the things that makes financial transactions different is that things are, to a first approximation, random walks. So essentially you got a one, in your Tesla example, you got a 1 out of 2 chance of being right. And then you specify, right over what time horizon too. So the likelihood of being right, 5 consecutive times is, like a couple percent or something.
But hold on, if you actually believe it's a random walk, then why are you even developing a predictive algorithm that beat the market, right? You're already assuming that's not possible in your premise.
Well, sort of in the absence of the model, that's what you would get.
Right.
But suppose there is a more intelligent way of uncovering patterns in the data.
Right.
But wouldn't that still mean that it's not a random walk? You just wrongfully were assuming it's a random walk?
Well, when we say random walk, we're always conditioning on information sets.
I see. Okay.
And what the statement would be is there is an alternative way of essentially looking at the data where you realize, it wasn't in fact a random walk. But because we didn't know this other stuff, we concluded it was falsely.
Okay. So I guess if you have like insider information, then it's not
That'd be a good
walk,
example.
Yeah. Okay. Fair enough.
Yeah. And insider information actually works.
If no new information emerges after the inside information is given to you, right? So,
but even though you got to be a little careful because there are groups, there are consulting firms that essentially try and infer inside information. Okay, so I mean, they will do things like, okay, so this guy's selling a chunk of his stock. All right. Let's go through the recent mortgage application records and see if he's buying a house. So they do things like that, or, their kids are going off to college, they're going to have these other expenses. So, I mean, there are parts of the insider trading that are predictable. And it's the other stuff that's... So, I mean, Elon Musk said he was selling, I don't know, 8 billion and change of Tesla.
Mhm. 4, I heard, but I guess maybe it's gone more.
Or 8, whatever it is. That didn't seem to move the market, and consequently, you know, the interpretation is that the market had already anticipated that.
Mhm. Because they knew he needed it to buy Twitter, for example, right?
Yeah.
Okay. Yeah, no, that makes sense.
Well, but again, I mean, your point is still valid because, you know, anytime we see a non-result, we simply say, gee, the market anticipated that. And that's kind of a weak null hypothesis.
But that information also propagated in the human domain, right? It didn't propagate into models. Models don't understand this stuff yet that I'm aware of. And so once again, we're in this kind of human machine model fusion situation where it's, you know, the human being is in the loop and is part of the story and right? So we can't just wave our hands and say, oh, the black box will work it out.
I guess the question is, what is the model? What could it actually learn? So, like, does it need all that details? Like, for example, like the model could learn in a time series of financial data, like something is going up and the rate of it going up is slowing down. Maybe that means it's about to go down. Then you should sell. Maybe it would learn it without knowing that you're even talking about price or time or people or any of that, right? And that in general might be true. So that's the kind of thing it would learn. But you're right that it doesn't learn that, okay, a slowdown in the raise in the prices means something to human beings, has something to do with their psychology. Maybe they get scared, maybe they start selling, like all this stuff you could put into the model if you want. But yeah, that's a different direction from trying to just throw the data into the black box, as you say, and see what it predicts.
Mm-hmm. Yeah. So is there a case for, okay, so there's a bunch of different, very useful conversation. I'm just trying to tease apart the questions. So there's 2 questions. One question is there a benefit in attempting to come up with the best explanation that we could understand for a given decision, given the amount of interest in explainability? I would say probably that's a useful thing to do. Given the EU requirements for understanding how your data is being used by companies is also potentially relevant, because this kind of technology could explain what is going on in terms of why the model made a choice that it did. Can it give you all 17 billion reasons? No, it can't, but it could probably give you a handful. And then you could...
I think there is one metric you should, I think it would make it super useful. Like it would convince me that the explanation generated is correct. Like let's say, going back to the Musk example, let's say the model says, dump all your stock because you ask for why. It says, because Elon Musk is going to resign tomorrow based on my prediction or whatever. And that doesn't happen, but you still make a lot of money because the Tesla stock is still should have been dumped for some other reason that the model didn't give you. Like if you penalize your model after this and basically say that explanation was wrong, and you keep improving your explanation until when you look back at them, they were correct. Like then I would start believing the explanations, right? If you give me explanations that apart from producing results end up being correct in retrospect, I think then then it would be super useful, because then I can maybe trust the explanation. Maybe you give me 5 reasons for any decision that the model is proposing, and I see that most of the time those 5 reasons end up being the correct ones based on like hindsight. I think then it would be super useful. Then I would totally take those into account.
Okay, yeah, all right. So that was one topic. And then the other topic, which is related but distinct, and I'm just trying to draw out the fact that it is distinct, is this idea of using closeness measures that don't involve a static metric, but instead involve I don't know what the right word is, feature, intervention, something. Essentially, we have observed in the past a state transition where the system went from this state to this state. Okay, and if we've observed in the past that the system was able to go from this state to this state, we could make the claim that there is a Markov chain of events, confounded, whatever you want, that enable that transition to take place. There is a precedent for this. There's this idea in category theory, which is you can set anything up you like, but if you can't actually create a thing in the category because there's no means by which you can create even one thing, then it's not real, right? So if we have a precedent, then we can make the claim that at least at that point in time, there was a process by which this system could move from this state to this state. It's possible that that could occur again. If we see that we're back in state one and we have a historical precedent of it moving into state two, then we can infer that there is a function or a mechanism or a process by which the system can make that state transition. And so we can infer an intervention exists. We don't know what it is, and that's not really important, but there is some series of things that could cause this state transition. If we study the data and we find a bunch of state transitions that relate this data to this data, and we find another bunch of state transitions that relate this data to this data, and they really don't have much interconnection between them as separate things, then we can call them separate things, right? So thingness is conditional independence, right? So we have no historical precedents of there being lots of state transitions that take these two systems between each other. In fact, we have none, or very, very few. So those very, very few, just to get back to my rant about affordances, are affordances, right? So if I'm in one thing and there is a very rare state transition that takes me from this thing into this thing, then we could say that that is distinct from, I don't know, it's very fuzzy. But that's where I'm trying to get to with the idea of state transitions being a metric of clustering.
But if you want to think about state transitions from like a category theory perspective, I don't know enough about category theory, but based on what you've taught us so far, like there is no time in category theory. There's no dynamics, right? So you just go from one state to the other. So I don't think you need all the language around it, even calling it state, calling it going from one place to another, calling it intervention. You just have two binary classification, basically. You're going A or B given your data. So that's all it is. Like the rest of it is, I guess you can talk about it, or maybe it gives you different approaches, but do you need to even formulate it in terms of Markov, in terms of states, in terms of interventions, in terms of conditional independence, in terms of thingness?
We're trying
all
to
that
infer
stuff.
The categories. Once again, we're hunting for equivariance. We're hunting for, I can just blob all these things together and just pretend that they're all cats. Good enough, right? That's where we're trying to get to. Okay, so what distinguishes you from me, right? There is an interaction. I could send you a letter with something in it, and you could hold it in your hand, or we could meet and have a cup of coffee, right? So we are interacting with one another, and yet we perceive ourselves as being independent to some large degree. That's what I'm trying to get at, right? So I am highly interconnected within me, and you are highly connected within you, and there is a weak connection between us, and it's that weakness and strength that I'm trying to characterize in some way. I
guess for real world objects, which I guess we are also examples of, like distance, like a real distance is a thing, right? Is a good approximation. Just the fact that you are many kilometers away and all your body parts are close together, that already clustered you into like an object that's separate, right? It didn't have to be like that, right? Like I could be in your brain, you could be in my brain, and everybody is in everybody's brain, right? And everybody's connected. Then in that case, there is no cluster, right?
Right, but in reality, there is, right? That something is going on, right? So I just think that is So you're saying it's distance again. I don't think it is distance. The point of what he's getting at in the free energy principle is trying to get at is he's trying to infer things from a morass of data in an unsupervised way. What he's saying is we've got some data, we don't know where the clusters are. If we identify state transitions in the data and we infer from those that there exists some process by which the system can make a state transition from this to this, then that tells us something. And if we collect lots and lots of data like that, then we can use that connectome or the structure of that connectome or the weights within that connectome to infer that we can call this thing a thing. Yes, everything's related and labels don't work, sure, but we're human beings, we need labels. So this is a human explanation thing. So we can apply a label to that thing, we can give it a name, and then we can make it one of these 7 things in our heads that we can actually understand.
No, yeah, I totally agree with you. I think that makes sense. I guess my point was, like, in real world objects, like real distance seems to be important.
That is one of the parameters, yes.
Yeah. But so in a general data set, like a financial data set, I see, so I think the problem reduces to finding the right distance metric so that to separate those things that are conditional independent. I don't know if you can just do that by using just the distance as a normal distance, right? Like the whole point is, what is that very, very complicated distance function that will separate out different things that you care about in this particular problem, right? Like, I think the way like he talks about it, the Carl Friston stuff is he's really focused on live, like living beings, right? Like in cells, so they have boundaries, so then they have sensors. Yeah, but in financial, like the entities we are looking for here are not living things. They're abstract things, so they're not real. You just want to separate them due to their usefulness, right? Based on something you want. So I think it makes it harder to find that distance, whereas a living thing is usually pretty contained in a small area, right?
The financial system is at the service of human beings who are things. Sorry to come back to this, but I think that you can't just wish away all the people. Rob, are there people who really put faith in black boxes and just hit a button and let it trade all their money away and assume that it's going to get better? Or I just don't think we're built to do that. I think that I would want to have a ticker on a wall where I can watch it go up and down and see what my machine's doing and shoot it in the head if it's being an idiot, or what I think is being an idiot, even if it's acting well.
Well, I mean, you know, some evidence of both. Yeah, I have seen entirely black box operations. And I've seen operations in which, you know, you make the human the black box. So, you know, you do what the human tells you, okay? And you know, is that really different from a black box? Well, I mean, maybe not.
But yeah, I think that's a great point. I think that's actually, I think you hit on the exact point I was trying to make. That, so I think, David, you said peoples are your entities, but I wonder if in a financial market, each person is not a relevant entity. I don't care what one person thinks. What you care is what the entire psychology of whoever is trading is. So I would say that people is not a good entity or a conditional independent entity when you care about financial trading. You care about something bigger and abstract. I don't know what it is. So you model the human psychology, or what do people do in a given situation on average. I think that's what you're trying to model. If you try to model every human being and their psychology, you're not going to go anywhere because it's irrelevant.
It's not irrelevant, it's just not accessible, right? It's too volatile to be of any value.
Sure. I mean, if in principle you could model every single person's like trading
in principle,
every given moment,
could.
Yeah, you could, maybe, yeah. But I'm just arguing maybe it's not super useful. Like in the same way, it's not useful to keep track of all the particles in the universe just to know if tomorrow it's going to rain, right? There's a lot of information there. Most of it is irrelevant. So you can do it if you had a really, really powerful computer, but you absolutely don't need it to predict whether tomorrow is going to rain or not.
Right. This gets us back to Feynman's path integrals again, right? So he's saying that there are situations where you do need to take the ludicrous step of essentially considering all possibilities and then having, you know, the stuff cancel out to see if there is an underlying trend that we could use to make a prediction. So,
well, one of the things that I was kind of puzzled about is, you know, what we're talking about here doesn't seem to relate real well to this concept of a Markov blanket. Because, or at least as I saw the explanation, it's not as, I don't know, maybe it needs a sort of a more comprehensive DAG or something, but sort of transitioning between clusters is hard to represent in that sort of blanket framework.
okay.
So am I missing something there?
No, I think I'm missing more than I think I am. I'm obviously missing some stuff here. So, okay, we keep coming back to Piam's very good, and quite frankly, I don't have a good response for it, argument that to some degree, everything is a black box, right? So sure, yes, we have to, you know, at some point, given incomplete information and also the possibility of new information arriving at any given point, we are still forced to make a decision, right? We have to either buy or sell or do nothing, right? We have to do something or nothing, but we have to make a choice, right? This gets back to decision theory. Making a decision in a fully connected connectome doesn't mean anything because it's not predictable, right? Because if you have some very, very, you know, tightly connected system, everything affects everything, and you know, prediction is impossible. So it's just, it is back to Rob's random walk. And I think the point of the Markov blanket is to say that we cannot generate meaningful human explanations in a fully connected connectome because there's no description that we could understand that makes any sense to us, right? So if we can have some sparsity, if we can simplify it, if we can essentially merge things together that are very similar so that we can reduce the complexity so that it is something that we can understand, then we can start to use our cognitive machinery around things and grasping and all the other stuff. But if we don't have that, then I don't know, it's just rubbish. So
this was the picture that I was thinking of. So the pink ones, the pink and the red parameter here, these are the Markov blanket. Oh, I guess without the blue. And then you've got your internal states and you got your external states.
Right. As I was going to St. Ives, I met a man with 7 wives. He had 7 wives and 7 cats and 7 cats and da-da-da. Right, so I'm generating an explanation. If I walk through the Markov chain, I can tell you a story about how we got from here to here. Okay, I think that's what he's trying to get to. Okay, why am I so fuzzy? It's very annoying. Sorry.
You look okay here.
Yeah, so what my understanding of what he's trying to get at is that the Markov blanket provides a countable set of steps that we as human beings can comprehend and understand. We have the cognitive machinery to interpret. And so it's us that's defining what things are. Things aren't things. It's just, you know, as Kant says, it's all in your head. So the benefit of the Markov blanket is that it is amenable to generating explanations that we can actually understand. And if we can clearly create an explanation that says that A is different than B, and we can say that there's a place called Sinai's and I'm not there yet, and I'm somewhere else, and I can get there, and Sinai's is a thing, and here I am, and I have to go on a journey to get from A to B, and I understand what a journey is, and I understand what a place is, and it fits into my head and my understanding. So I think that's what Friston's about. It may not be useful in economics, and I completely accept that. And maybe I'm misdirecting us, Rob, and I should stop and just go back to the data. And that's a genuine concern I have. So yeah, that's kind of my take on why he thinks that Markov blankets are relevant. I don't think there's some deep underlying thing that's in the universe. I think there's some deep underlying thing that's in our brains.
I mean, I think the Markov blanket, like it's sort of only relevant at high level. Like if you are a trader, I would say your Markov blanket is your brain and your sensory organs is whether to trade or not, your affordances, right, in actions you can take. And then it's you versus the outside world. So everything else, the whole trading market is in the external states of the system. And it's not, I guess, very useful, but it's sort of one way to... But yeah, I don't think you can go into the financial data and define a Markov blanket. Like, I don't see how that's relevant. There might be some, basically that's what we are trying to figure out.
Give you a 2-second intro into what I was thinking. Mm-hmm. So on that, so there's always the possibility of surprise, which is information that was not in the past data set, or we've forgotten it or something, right? So some event occurs for which there was no historical precedent. No model I've ever created could predict it because I don't have any past anything. It's not sure, right? So if I go into a restaurant and I choose the chicken or the fish, I don't know. You know, there's so many different factors there. I really don't know which way it's going to be. But the fact that I went into a restaurant is known, and the fact that there are 2 counterfactual universes that I could move into from there, or n fixed number of counterfactual things I could move into there, says that if I see somebody walk into a restaurant, I can honestly say that the amount of fish that will be left in the fridge at the end of the day is uncertain. And every time somebody walks into the restaurant, the uncertainty about how much fish will be left at the end of the day will go up, if you will. Mm-hmm. Yep. And so this is actually telling us something. It's not telling us much, but it's saying that accurate prediction of something given this precursor has gone down, right? Or if we see something that always follows something else, right? So if I don't know, you know, some obvious A-B thing, right? If I light a match and it catches on fire or something, I don't know. But if there's only one possible outcome and I see a precursor, then I can very confidently say that I have no historical precedent of this being anything other than this. Does that make sense? So that there's nothing in my memory that I can recall that says that this should behave in any other way than the way that I've only ever seen it occur. Mm-hmm. Right, so the sun comes up every day, and therefore, you know, Hume's problem of induction is going to come up tomorrow. And I have no historical precedent of it not happening. Therefore, unless there's some new piece of information, some surprise, the sun goes out or the earth starts to stop or whatever, some crazy outcome, I can make a very confident prediction. Do you see the distinction? So if I see a precursor that leads to a choice, then I can honestly say that uncertainty about my choices has gone up, and then I can essentially hedge that. So I could have extra fish and extra chicken, or I could make a choice and just throw the dice and gamble. It really.
But isn't that what predictive models are trying to do? Like you're doing that with one parameters. We can do that in our head.
Typically, that I've seen try to make predictions. So, and I know that sounds very glib, but I'm not trying to make a prediction. I'm trying to either make a prediction or say, I don't want to make a prediction because I don't know. And how does the machine know that it doesn't know? Right, so, yeah.
Well, it does know. It's just we ignore that information.
I mean, in statistics, you have confidence bounds, right? And with probably with the farther you go down your time horizon into the future, that error bound increases and increases. Whether or
Yeah.
not that's accurate enough, I don't know, but
yeah, I mean that's one way to think about it in a categorical sense. I don't know. Suppose you have your logit function or your hyperbolic tangent function. So when you're right close to the middle, so on a logit to be 0.5, on a hyperbolic tangent and be 0. If you're close to 0, you're going to get classified as either a -1 or a +1. But there's a lot of imprecision in that. If you're out in the tails of that, you're going to get classified much more accurately. So the model is kind of taking that uncertainty at the end and sort of tossing it aside for the purposes of generating a classification.
but
So it is there, but we just kind of.
But I don't think logits are like, they're technically not probabilities, right? We just make them into probabilities by normalizing them between 0 and 1. So they're not actually reliable, and you can test it for yourself. Like if you take a neural network, right, with the weights, and let's say you get some classification, cats and dogs, if you multiply every weight in the neural network by a constant, like 2, all your probabilities change and the results stay exactly the same. And that's one simple demonstration to show that these are not real probabilities. You just basically, you can scale it arbitrarily. So you can totally have something that has very, very high confidence and be completely wrong, and have something that's very, very low confidence and be right most of the time. So yeah, logits as probability confidence is not a good way of like assessing. People do that, but it's not a good way. Because those are not real probabilities. It's just we make them look like probability by just normalizing them.
All right, we're over time now, but yeah, I want you to walk through that example with me at some point.
Yeah, for sure.
Okay. A very, very interesting conversation. So I just want to clarify, am I off base in thinking that the explainability stuff is relevant or not? I think I might be.
No, it's a huge field, right? Like lots of people are working on it. It's a big concern. Like you mentioned, like the regulatory agencies. Yeah, I just find it's just my personal bias that I don't think any of this stuff is going to go anywhere, because an explanation I get off of a human being is not reliable either. It's just we feel like we're being hypocrites and demanding something from the algorithms that we can't even demand from ourselves. Like, but I think you probably 99% of the people agree with you, David, that explainability is extremely important in AI, and I'm actually working on a survey paper with a bunch of people on explainable human in the loop systems. And I'm finding it very difficult because that's the whole point of the paper, but I don't believe in it. So I think human in the loop systems, you can do just fine without any explainability. The same way I can work with you without knowing exactly why you do things. I just sort of observe what you do and learn and adapt to what I can expect from you without knowing the reasons of why you do something or you say something. But that's just my bias. So
no. But okay, that's very. I know we're over time, but I just want to kind of go into this a little bit deeper. So you're saying then that we should be building machine learning systems that give us prediction, not explanations, right? That you see more benefit.
Like, not necessarily. Like prediction is important. I think you want trust. I think that's people want to use explanation as a way to build trust. But for me, I'm saying that doesn't make me trust anything. What makes me trust, like working with you, David, is we work a little bit. I learned to predict what you would do in a given situation. I know you're not going to stab me suddenly. Like eventually we develop trust. And then I develop my own model of how David thinks, and this is the explanation. I don't need for you to generate explanation for everything you do for me to trust you. I just need to like have consistent performance. Like that would be the prediction coming out of you that I think makes sense. Maybe 90% of the time I know what David says makes sense. So then I end up trusting you. And that's how human beings interact with each other. I don't think we need to go inside each other's brain and generate explanations to build trust.
Is it useful to build trust with AI, do you think?
Absolutely. Like if you are like we are, so this paper that I'm working on, they want to basically do farming equipment that is semi-autonomous. So they want to like do things like robots that are working alongside human beings on farms. So obviously you need to trust that the robot is not going to kill you. It's going to be predictable. And if you do something, you can expect that it will do something that you expect. Like that's how trust is built. Like how it does it, I don't care. Like as long as it does it reliably, like in my thermostat, I don't need to know and see all the like why it's raising the temperature at what rate and all that. As long as it does what I want it and it does it consistently, and I can predict that if I set the setting point to 30 degrees, it's going to start heating. If I set it to 0 degrees, start cooling. That's all I need to know.
Well, okay, so here's part of I think why you do need to go deeper. So if I would look at, say, economics, finance, sociology, empirical work in that area, you know, you give me any published paper and I could probably reverse the results of that. Now, how would I do that? Well, you need to give me flexibility on which variables to include, which time periods, you know, those are and maybe some methods. So I could take anything from being probably significant to probably insignificant and perhaps even significant the other way.
I believe you. Yeah, that's the big problem. But that's not the explanation is not gonna help you. Like an example is this, have you seen this?
No, but it would.
Yeah, but you can generate explanations for after you change your result. You can again generate explanations that are very reasonable. So how do you trust those explanations? Like I don't.
Well, that's kind of my point, is that's why you want to pay attention to things, because the explanations are themselves kind of a black box.
Yeah, I think that's a very good point. Like, that's basically my point. I think that's a good way of saying it. The explanations are just as black box as the other ones, except they're put in a beautiful language that human beings like their stories, and they tend to make you trust them and believe them.
And that's the mechanism that is in our DNA, and we have to live with that, right? We could kind of wish it away and pretend that it's not there, but at the end of the day,
but you know, doggone, it's worked pretty well. So
yeah, but somehow we're okay with it. But we're okay with it coming from human beings. Like there's these algorithms that do like judgments on parole, right? Like whether somebody should be paroled early or not. And people are saying, oh, we can't use them. Like we need to know why. But if you go look at the judges who give paroles or not, they're racist, they're sexist, they're hungry, they're tired, they just want to go home. And if you ask them, why did you parole this guy? They immediately give you a very plausible answer why they did. They're never going to say I was hungry, I just didn't care. So, I mean, how is this any different? That's why I think it's a little bit hypocritical to want like transparent AI models as opposed to transparent human beings, right? We're just never going to get either of those.
But I accept your argument, and my counter argument, which isn't very strong, is that even then, explanations are still part of the story, because we have this system 1, system 2 thing where our intuition tells us one thing, but if our system 2, if our system 2 can't corroborate our feelings with a good explanation, then typically we don't proceed. So you have to have both boxes ticked. There has to be an intuitive history of, so this kind of non-verbal belief that the model is doing what you want it to do. And system 2 also has to buy the car, right? And so you need to provide food for both, right? So you need to have historical precedents that are known to you, and a trust and all these other things, which are very system 1. But at the end of the day, if you go in and you say, oh, I really like this car and it's lovely, and then system 2 says, oh, how much does it cost? Oh, it's only $1.2 million. We don't buy the car.
I totally agree. So,
right?
But then the problem reduces to like, okay, given the human psychology, if you want to sell something, how do you approach? Then I totally agree with you that we need to generate some plausible explanation. I'm just saying that that's
as
not
well
possible.
As actually having value. Just the explanation isn't enough either, right?
Sure,
So,
the value would be the predictive part that, let's say, we know how to do, right? That's your model that gives you 90%, but we say that's not enough. We need a story to go with it. I mean, as long as we agree that that story is bullshit, it's just there to hack the human psychology so that it develops trust, I'm totally with you. I'm just saying that that explanation, I don't personally trust because I think it's like made up.
Well, but now we're getting back into the realm of science. I mean, there are lots of examples where, you know, people have done things that seem to work and therefore had predictive value. And we, you know, essentially we discovered that they're not right. I mean,
but in science, you get one thing that really helps, and I don't think it's not really possible to get it in like a general domain. Is like if I come up with a new theory, which is an explanation that maybe is bullshit, like nobody knows, but then I come up with also an experiment to falsify or verify what I did, and it's an experiment that goes against every other explanation that we have. Then you go do the experiment and, oh, it turns out my theory was right. Then it's a huge evidence for it, right? Because I hadn't done the experiment, I didn't have that knowledge. I made I staked my whole explanation on one thing that can be verified. Like, but can you do that in everything? I don't know.
Yeah, I'm not trying to be a dick, but my counter argument to that is that that's just pandering to system one. Right, you know, oh, you know, if I show you this thing and it goes up here and it turns blue, then, you know, so it's just
but
an explanation of a different sort. So
no, but it could be like a whole elaborate theory without, like in some cases, without any tuning parameters, right? Like most of science doesn't have tuning parameters.
Exactly, I understand. Yeah.
Yeah. So if that turns out not to be blue, like the entire thing is wrong. And I guess you can never prove a theory, right? So if it turns out to be blue, you can say, okay, to have some evidence. But if all the other explanations say it should have been green and you made it blue, I think that's the art of the science, right? Like how do you design an experiment to really separate out different models or different explanations, right?
Yeah, we can wind it up. I do think, though, that I'm going to cling on to this idea that generating explanations or simplifying models so that they're comprehensible does have a net benefit in a human-computer loop. I think we could make that claim reasonably. Would you agree?
Yeah, I mean, I agree. Yeah, for sure.
Okay. Yeah, and you know, again, my favorite example is celestial mechanics. So the pre-Copernican view of the world had, you know, the planets revolving around the Earth, and in order to
epicycles.
Yeah, they had cycles and they had epicycles, but it worked really well.
To this day, people still use it because it gives really good prediction. Like for navigating in the oceans, people still use that model. Right? So yeah.
But so you know, it fit the data. It generated a great prediction.
And it was explainable, right? I could build a model. I could physically ding, 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 like build. That's the picture I showed a couple of weeks ago, right? Of the Copernican thing, right? Because it's comprehensible. I can do this, right? So
yeah. I guess, you know, the punchline where I come away, at least with this part of the discussion, is yeah, we got to be careful about explainability.
I mean, that's why I like that, like closing the loop, right? Let's say you generate explanation. I say fine. But then every once in a while, we'll go back, look at your explanation and see if it actually made sense given what we learned since. And if it doesn't, then you go give me another explanatory model because your original model was wrong. Like as long as there is a chance, opportunity to correct and improve the explanations in a systematic way, I'm with you. But if it's just something that's generated and there's no way to verify it, I'd rather not have it actually. I don't think it adds any value for me.
But okay, I struggle with that. You have a way of explaining the world, as do I. I'm not trying, like I have a way of explaining the world in my own mind, and I use those explanations. I don't buy $1 million cars because I can't afford it, and that's not my intuition. I'd love to have $1 million car, but so, you know, in some perfect world, yes, we wouldn't need explanations because we wouldn't be bounded by our, you know, evolutionary history. but we are. It's my kind of counter argument. So we kind of have to fit into what we've got. But yeah, it's an interesting question.
Yeah, but I think we agree that like a bad explanation is worse than no explanation, right? Or do you think that that's not true?
Bad experiment.
Bad explanation.
So let's say like your stock, whatever thing says, I think you should sell your Tesla stock because it's cloudy today. And yes. I think whenever it's cloudy, you should sell your Tesla stock. And if you believe it, I mean, I would say like that's worse than saying nothing and saying, I think we should just sell the Tesla stock and I'm not going to tell you why. And it's 90% correct.
Okay, because, well, this gets back to the reward function of the model actually incorporating the human as a factor, if that makes sense. So its choice to provide that explanation versus this explanation should also be part of the training set. Right, so it's training you to agree to explanations that have predictive power, and it's trying to avoid giving you explanations that don't have predictive power or intuitive predictive power, because the purpose of providing the explanation is to trigger you to make a decision one way or the other.
Is it? Right? Okay, so that's a bigger disagreement. So I think the purpose of the explanation should be to give you some truth about the world that's behind the actual prediction value, not to convince me to do one way or another. That's marketing. And then I really don't want that explanation.
Fair enough. Okay, no, okay. But there was another part to that. That would lead you to a null result, right? So if I look at the advertising, I say, oh, that's a great deal, and I click on it, I learn very quickly that it wasn't a great deal. So what I'm saying is that a virtuous API, AI, would try to provide an explanation that would drive you to the outcome that is best for you, according to the value function that you gave it.
Right? I totally disagree with that. I really don't want the system to decide what's good for me and then come up with ways of convincing me to do it, even if the outcome is positive for me. I think I need to decide whether I want an outcome or not, and the explanation should be aligned with the truth to this extent that's possible by the model.
Personal not truth or objective truth.
No, there's objective truth, not a person. There is no such thing. I don't know what the personal truth is. I'm talking about objective truth.
So I don't believe in objective truth. So.
Okay, so that we're going way back into the, if you don't believe in objective truth, then that's a different discussion.
So maybe we'll have that discussion next time. But yeah,
I gotta go.
Yeah, take care.
Okay. Take care. See ya.